correctly sized conductors and overcurrent protection devices, or OCTs, according to the National Electrical Code. Consider a scenario involving a 4-wire, 3-phase Y75°C panel board with a continuous 190 amps load operating in a 30°C ambient temperature. The initial step is to determine the minimum overcurrent protection device size. According to the code, specifically sections 215.3 and 384.16 paragraph D, the overcurrent protection device must be rated for at least 125% of the continuous load. Therefore, 1.25 multiplied by 190 amps equals 237.5 amps. Referring to section 240.6, which lists standard overcurrent protection device ratings, the next standard size up from 237.5 amps is 250 amps. Thus, a 250 amps overcurrent protection device is the minimum required. Next, the conductor size must be determined. Section 215.2 mandates that the conductors must be rated to carry at least 237.5 amps, which is 125% of the continuous load. Further, Section 110.14 paragraph C specifies that for termination temperature limitations, the 75°C ampacity rating of the conductor should be used, unless equipment is marked otherwise. Consulting Table 310.16, a 250 mcm copper THHN conductor has an ampacity of 255 amps at 75°C, which appears to meet the requirement. However, it's essential to account for ampacity derating if multiple current-carrying conductors are bundled together in a raceway or conduit. In this scenario, there are 4 current-carrying conductors in the conduit. Table 310.15 paragraph B3. A outlines the ampacity adjustment factors for multiple current-carrying conductors in a raceway. Using this table, with 4 conductors, the ampacity must be derated to 80% of its original value. When applying derating factors, you use the 90°C column for the initial ampacity value, as per the instructions of 110.14 paragraph C. The 250 mcm THHN conductor has a 90°C ampacity of 290 amps. Applying the 80% derating factor, 290 amps multiplied by 0.8 equals 232 amps. Now, consider the critical point. While the 250 mcm conductor has a 75°C ampacity of 255 amps, seemingly sufficient for the 237.5 amps requirement, the derated ampacity is only 232 amps. This is less than the required 237.5 amps. Therefore, the 250 mcm conductor, even though it initially appears adequate, is not suitable after applying the derating factor for multiple conductors in a raceway. Section 240.3 paragraph B permits the use of the next higher standard overcurrent protection device if the conductor ampacity, after derating, does not correspond to a standard overcurrent protection device size. However, this allowance does not supersede the requirement to have adequate conductor ampacity for the load. The conductor must be sized such that its derated ampacity is at least equal to or greater than the calculated load current of 237.5 amps. In this case, you must increase the conductor size. To determine the appropriate conductor size, consider the next largest standard conductor size, which is 300 mcm. A 300 mcm copper THHN conductor has a 90°C ampacity of 320 amps. Applying the 80% derating factor, 320 amps multiplied by 0.8 equals 256 amps. Since 256 amps is greater than the required 237.5 amps, a 300 mcm conductor is adequate for this application. Now that the conductor is correctly sized, revisit the overcurrent protection. The initial calculation called for a minimum 250 amps overcurrent protection device based on 125% of the continuous load. Since the 300 mcm conductor has a derated ampacity of 256 amps, a 250 amps overcurrent protection device can be used. The code allows for the overcurrent protection device to protect the conductor at its ampacity. In summary, for a continuous 190 amps load on a 4-wire, 3-phase Y75°C panel board with full current carrying conductors in a raceway in a 30°C ambient temperature, use 300 mcm copper THHN conductors protected by a 250 amps overcurrent protection device. This ensures compliance with the National Electrical Code and provides a safe and reliable electrical installation. The National Electrical Code, or NEC, is a comprehensive set of standards and guidelines for safe electrical installations. It's published by the National Fire Protection Association, or NFPA, and is updated every 3 years to reflect changes in technology and best practices. Understanding and adhering to the NEC is crucial for electrical engineers, electricians, and anyone involved in electrical work to ensure safety and prevent electrical hazards. One of the most important aspects of the NEC is conductor sizing. Correctly sizing conductors is essential for preventing overheating, voltage drop, and potential fire hazards. The NEC provides detailed tables and calculations to determine the appropriate conductor size for various applications. Key factors influencing conductor sizing include ampacity, which is the current carrying capacity of a conductor, temperature rating, which specifies the maximum operating temperature of the conductor, and derating factors, which account for conditions that reduce the conductor's ampacity. Article 310 of the NEC covers conductors for general wiring. This article provides requirements for conductor insulation, ampacity, and installation methods. Table 310.16, also known as the ampacity table, is a fundamental reference for determining the ampacity of conductors based on their size, insulation type, and temperature rating. It lists the allowable ampacities of insulated conductors rated up to 600 volts, based on various insulation types such as THHN, THW, and XHHW. When using Table 310.16, it's essential to consider the conductor's temperature rating and the ambient temperature. The ampacity values listed in the table are based on specific temperature conditions, and adjustments may be necessary if the actual operating conditions differ. Section 110.14 paragraph C addresses the termination temperature limitations for conductors. This section specifies that conductors must be selected and installed so that their temperature rating is not exceeded. Typically, equipment terminations are designed for 75°C conductors. Therefore, unless the equipment is marked otherwise, the 75°C ampacity rating should be used. Derating factors are applied to conductor ampacities to account for conditions that reduce their current carrying capacity. These conditions include high ambient temperatures, multiple conductors in a raceway, and the presence of harmonics. Table 310.15 paragraph B3 provides ampacity adjustment factors for multiple current carrying conductors in a raceway or cable. When multiple conductors are bundled together, the heat generated by each conductor can raise the overall temperature, reducing their ampacity. The adjustment factors in this table are based on the number of current carrying conductors in the raceway. For example, if there are 4 to 6 current carrying conductors, the ampacity must be derated to 80% of its original value. Ambient temperature correction factors are used to adjust conductor ampacities for high ambient temperatures. The ampacity values in Table 310.16 are based on a specific ambient temperature, typically 30°C or 86°F. If the actual ambient temperature exceeds this value, the conductor's ampacity must be reduced using the correction factors provided in Table 310.16. Overcurrent protection devices, or OCs, such as circuit breakers and fuses, are essential components of an electrical system. Their purpose is to protect conductors and equipment from overcurrent conditions, such as short circuits and overloads. The NEC provides detailed requirements for selecting and installing overcurrent protection devices to ensure proper coordination and protection. Article 240 of the NEC covers overcurrent protection. This article specifies the requirements for overcurrent protection devices, including their rating, location, and application. Section 240.3 addresses the protection of conductors. This section requires that conductors be protected against overcurrent in accordance with their ampacities. The overcurrent protection device must be sized to protect the conductor from damage due to overcurrent conditions. Section 240.4 paragraph B permits the use of the next highest standard overcurrent protection device rating if the conductor ampacity does not correspond to a standard overcurrent protection device size. However, this allowance is subject to certain limitations and conditions. The next highest standard overcurrent protection device can only be used if the conductor is part of a multi-outlet branch circuit supplying receptacles for cord and plug-connected portable loads, or if the ampacity of the conductor is not less than the rating of the overcurrent protection device. Continuous loads are defined as loads that operate for 3 hours or more at a time. The NEC requires that conductors supplying continuous loads be sized to carry at least 125% of the continuous load current. This requirement is intended to prevent overheating of conductors due to prolonged operation at high current levels. Sections 215.2 and 215.3 address feeder conductor sizing and overcurrent protection for continuous loads. These sections require that feeder conductors supplying continuous loads be sized to carry at least 125% of the continuous load current. Similarly, the overcurrent protection device for feeder conductors supplying continuous loads must be rated at not less than 125% of the continuous load current. The NEC also provides specific requirements for conductor identification. Conductors must be properly identified to indicate their purpose and function. This is essential for safety and troubleshooting purposes. Section 310.8 addresses conductor identification. This section specifies the methods for identifying conductors, including the use of color coding, marking tape, and other means. Grounded conductors, also known as neutral conductors, must be identified by a white or gray color. Equipment grounding conductors must be identified by a green color or a green color with one or more yellow stripes. Ungrounded conductors, also known as hot conductors, can be any color other than white, gray, or green. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC provides recommendations for minimizing voltage drop in electrical systems. Informative Annex D provides guidelines for calculating voltage drop. This annex recommends that voltage drop on feeder and branch circuit should not exceed 3% and that the total voltage drop from the service entrance to the furthest point on the circuit should not exceed 5%. To minimize voltage drop, conductors with larger cross-sectional areas can be used. Larger conductors have lower resistance, which reduces voltage drop. The length of the conductor run should also be minimized to reduce voltage drop. Proper installation techniques are essential for ensuring safe and reliable electrical installations. Conductors must be installed in accordance with the NEC and manufacturer's instructions. This includes using the correct wiring methods, supporting conductors properly, and making secure connections. Article 300 of the NEC covers wiring methods and materials. This article specifies the requirements for various wiring methods, including conduit, cable, and surface raceways. Conductors must be installed in accordance with the requirements for the specific wiring method used. Proper grounding and bonding are essential for electrical safety. Grounding provides a low impedance path for fault current to return to the source, which helps to trip over current protection devices and prevent electrical shock hazards. Bonding ensures that all metallic parts of an electrical system are electrically connected, which minimizes the risk of voltage differences and electrical shock hazards. Article 250 of the NEC covers grounding and bonding. This article specifies the requirements for grounding and bonding electrical systems and equipment. A grounding electrode system must be installed to provide a connection to the earth. This system typically includes a grounding electrode conductor connected to a ground rod, metal water pipe, or other approved grounding electrode. Equipment grounding conductors must be installed to connect metallic equipment enclosures to the grounding electrode system. This ensures that equipment enclosures are at the same potential as the earth, which minimizes the risk of electrical shock hazards. In addition to the specific requirements discussed above, the NEC also includes general requirements that apply to all electrical installations. These requirements are intended to ensure safety and prevent electrical hazards. Section 110.3 addresses examination, identification, installation, and use of equipment. This section requires that electrical equipment be installed and used in accordance with its listing and labeling. Equipment must be suitable for the intended use and installed in accordance with the manufacturer's instructions. Section 110.9 addresses interrupting rating. This section requires that equipment intended to interrupt current at fault levels must have an interrupting rating sufficient for the nominal circuit voltage in the current that is available at the line terminals of the equipment. This ensures that equipment can safely interrupt fault currents without failing. Section 110.12 addresses mechanical execution of work. This section requires that electrical work be performed in a neat and workmanlike manner. This includes properly supporting conductors, making secure connections, and avoiding damage to equipment. The NEC is a complex and comprehensive document that requires careful study and understanding. Electrical professionals should be familiar with the NEC and stay up to date on the latest changes and revisions. Continuing education and training are essential for maintaining competency in electrical work. The NEC is intended to provide a minimum standard for safe electrical installations. Compliance with the NEC does not guarantee that an electrical installation is free from all hazards, but it does significantly reduce the risk of electrical shock, fire, and other electrical hazards. Electrical installations should be designed and installed by qualified professionals who are familiar with the NEC and have the necessary skills and experience to perform the work safely and correctly. Always consult the latest edition of the National Electrical Code for specific requirements and guidance on electrical installations. Remember that local codes and regulations may also apply, so it's essential to check with the local authorities for any additional requirements. Staying informed and following best practices are crucial for ensuring electrical safety and preventing electrical hazards. Firstly, always prioritize safety when working with electricity. Secondly, ensure compliance with the National Electrical Code. Thirdly, use appropriately sized conductors and overcurrent protection devices. Fourthly, consider derating factors for multiple conductors and high ambient temperatures. Fifthly, properly ground and bond electrical systems and equipment. Sixthly, stay up to date on the latest changes to the NEC. Seventhly, seek continuing education and training to maintain competency. Eighthly, consult with qualified electrical professionals for complex installations. Ninthly, perform electrical work in a neat and workmanlike manner. Tenthly, regularly inspect and maintain electrical systems to ensure their continued safety and reliability. The importance of accurate calculations and adherence to the NEC cannot be overstated when it comes to conductor sizing and overcurrent protection.